Hi, this is Bill Foote, and this is week 7. Oh no, week 6. I'm already thinking about week 7 uh, of our decision modeling with spreadsheets course. We are putting Excel and ourselves to the test. I want to immediately share my screen. Welcome, by the way, to this week. It's a little late in coming, but it is here finally. I have a simulation 2. I'm calling it the Outer Limits, and I immediately jump ship from that program into the Twilight Zone. So I'm going to be finding typos, I'm sure. We're looking at the tails of distributions. That's the thing that really bothers us in managing practically anything. If they're thick tails, that means something can happen. And if it happens, we better be prepared. It doesn't happen frequently. Frequently doesn't matter now. It's the fact that it happens. And can we simulate those sorts of issues? One of those is workers' compensation claims. This analysis here is based upon work I did with Minnesota and California, not New York. New York has a little bit different approach to life here. But our vegan company, Make a Pie, has gotten together with a group of other vegan food facility owners. They too make vegan foodstuffs as well as have restaurants. They're all meeting at Candle Cafe. Candle 79 is closed permanently. And that is a premier vegan restaurant with a very big vegan cookbook. They pioneered a lot of, for example, French cooking, Mexican cooking, German cooking, you name it, they've got it, and they're expanding in a number of different directions, very much influenced by Hindu cooking and some African cooking too, West Africa, probably Cameroon. So this is very interesting, but they're getting around and they have this meeting where they're discussing issues and they're sharing stories, and some of them are in competition with each other, but their employees are or are not. I mean, the employees shift from place to place, just like in the Silicon Valley approach to life. They're experiencing very high costs, and some of those costs are ballooning unexpectedly. Okay, so even the notion of an expectation is changing in their minds, and they want to model this. They want to do something different. What they want to do actually is self-insure. Let's look at self-insurance, or at least some way of countering what the New York State Insurance Fund is doing and their policyholders with that. So they will go out and they hire us, okay, to look at some data, and it always starts with data. Well, it doesn't. It's actually starting with this meeting and a question about a particular issue. And that's a misstatement, actually. It doesn't always start with data, but our analysis will after the question has been posed. We have gross claims. These are a small sample, $107,000 up to $1,203,000 is a $675,000 and an $870. Oh my, okay. So the first thing that we do is we look at a little time series and we see there is a regularly occurring background scatter of low-level claims that are probably covered by insurance fairly well. But then we have these huge jumps every now and then. And we do a little bit of an analysis of it, min, max, there it is. And something called Tukey, John Tukey, 1977 exploratory data analysis, outlier analysis. And what he does is he says, okay, and it's more of an example. Take the 25th percentile, the 75th percentile, add the difference between the two. That's called the IQR. It's $169,000 worth of difference. And that is actually a more robust nature, better than the standard deviation which Ronald Fisher and others were contending with in the 1920s. And we're just rediscovering it. Because we have textbooks with this, but we don't use it. Okay, we're going to use it here. Don't worry about these other categories here. It's all very interesting stuff. 2 and 13.5 and 0.06. What the heck does that mean? We will find out very soon. But we take 276 and add 1.5 times 169 to it, and we get 529. So 529 is up here. We could well have mapped that, and you'll see it absolutely finds these outliers. Now, how do you model the outliers with such little data? How much data would you need to have? Oh my gosh, this isn't working either. I'll have to fix this someday. Sorry about that. Don't worry about this metric. The metric is down here. I don't know what the heck happened here. Anyway, what I will do, let's see here if that's over here. No, we got rid of it. Okay, I'll figure that out someday too. Just a little bit of algebra here. Don't worry your heads over this, but it's a good flexor. In the business of business analytics, and decision analytics especially, we end up needing to use this. And when we look at the expected value of any excess of a claim, that's X, over a threshold, we're looking at the expectation of it. Okay, so we calculate that, and we find that that excess of a claim, the average excess of a claim over a threshold is nothing more than the mean of the claim minus the threshold. Okay, I mean, we're just playing with this a little bit, but here's the excess of a claim over a threshold. Now, why are we doing that? Because, well, we saw a threshold there. It's about 100,000. And now we're looking at any claim in excess of that. That's the one that's worrying us. That's the one we're going to jump to. That's why we're doing it. Okay, so there's some math here. Again, let's not worry ourselves. Oh, yes, it's a nice algebraic exercise, so on and so forth. But what's interesting about the algebraic exercise is that the variance, which is the square of the standard deviation, is equal to the variance of the claim itself plus the square of, I mean, this is almost Pythagorean theorem, but corrected for some interaction between the mean and the average of 2 times actually of the threshold. So it's a little bit more complicated, and that's our first hit. My God, it's going to be complicated. What are we going to do about this? Okay, so we do some calculations, and this takes one line of code anywhere else, even in VBA. The first thing we do with the claims is we order them from lowest to highest. And then we perform a calculation for each threshold. I'm going on a threshold here with a minimum of 200 and a maximum of 1,000. So that kind of gets us into the relative ballpark here. Yeah, roughly 2,000. There we go. That's okay. And a maximum of 1,000 up here. Okay, fine. So we're going to be looking at all the ways in which these numbers, and these will all fall short of that. But this one won't, that one won't, that one won't. Okay, these are all ways of managing this kind of thing. And we can use other thresholds as well to examine this. So we have claims. And you see that the only excesses are down here. And we get an average. And then more excesses. Everything else is just zeroed out because it's the max of 0, or, I mean, it's not excessive. It's not excessive. And it keeps going down here. And then we begin to lose some followers here. There we go. We lost one, and we're all the way down here to this. Okay, and we can map this into a cute little drawing which shows the excess of threshold for all of these claims is linear up to this point, and then it gets kind of weird. A little bit of turbulence begins to occur. So the maximum threshold is around 400 in which we see things happening, but it keeps getting lower, and the excess gets lower and lower till it hits here. This is a very common framework, and people use it to say that there's a distribution in which this will map to very nicely. And this is a distribution to remember. Here are our three asks, if you will. One, the distribution has to be able to handle those 100,000 plus or minus. It has to be able to generate that. But it also has to be able to generate, on occasion, and this is kurtosis. Kurtosis is volatile standard deviation. That's really what it is. Measures the thickness of the tail. We got to be able to get a distribution that generates very high outcomes on occasion. I mean, very high outcomes. And we will see how that works. But it also has to be easy enough to implement so that we can get an average, a standard deviation, a correlation eventually, all those sorts of things. Here is such a function. It's called the generalized Pareto distribution. You can click on these to get a little bit of background reading on it. Very useful. Wilfredo Pareto also had some fairly extreme ideas about economics and who should be ruling. I think most economists should be staying out of politics. That's how I look at it these days. So we'll take mu as a threshold, and here's x minus mu over sigma inside the formula. That's a z-score. We center the claim around the mean, take that deviation relative per unit of standard deviation. That number will always, if you sum up x minus mu across all the claims, it is always 0. And this z-score will always have a standard deviation of 1. And it's commonly used, and we use it a little bit, the idea behind it, with the Cholesky transformation, factorization, regularization, a lot of names for it, last week. But here we have the probability that we see a claim, and the bar means given these three items, which effectively are conjectures, they're hypotheses. And it has this lovely form, and notice a little plus sign here. This thing always has to be positive, all right? Otherwise it's negative. Mu is always positive, thresholds are always positive. Standard deviations are always positive by construction. And we use this notation. Now, this C thing is the shape of the distribution. And C, let me just bring up a quick drawing here. That's one possible C. Another possible C. So that parameter tells you how much curvature there is. More C, more curvature, less C, less curvature, okay? And look, it slopes down at a slower rate to what? The really large, big claims that we hope never happen, because otherwise we're going to go into receivership. Now this orange curve here is sloping down pretty fast. So if your maximum claim is here, it's a matter of how fast will this distribution get there. This is going to be the distribution to forecast, otherwise project, what future claims will look like. That is what we're after. When we know future claims, then we'll have a rough idea about how to prepare for them. How would we prepare for them? We would prepare for them First of all, we have to know when they might come. So that's problem number one. Problem number two is not only when they come, how big will they be? So if we go like 100, and then a huge number like 8,000, okay, which is 8 million in this case, you know, we have to prepare for it. How do we prepare for it? We invest premiums that we collect among our little group of vegan self-insurers to manage the possibility of that. That's what we do. Now, the problem is we don't know whether it will happen or not. So we're going to run a lot of simulations to see how big it could be on average, how much variation it could be on average. Okay? We can even go further to see if 1 year or another of claims is related, as a correlation of some sort. We could do that. We're not going to do that here. That's a little bit more complicated. That would be an interesting time series analysis problem. But we go back to our analysis here. This equation allows us to do that. And then I get a little bit more crazy stuff there. Now, the law of conditional probability, which I also have underscored here, is something else that happens. We're looking for a both and event. We're looking for a piece of data, a claim, that's happening at the same time as a conjecture. And we want to find out what is the probability of seeing a large, a small, a medium claim. We have our data for that. And at the same time, see a particular scale, that's sigma, or dispersion of claims, standard deviation, or that shape I was talking about, that knee that comes down, more curvature, more C. We're going to find out that sigma is going to be about 13.5 thousand. We're going to find that C is about 2, which has no real meaning whatsoever until we begin to simulate with it. So we build a grid with this thing. Whoa, don't get too close. It's an eye test. We have hypotheses. We make a grid, and we basically are using if statements and index and match to do this. So it's an interesting approach, but basically for each C level, so we have to project a low Z equally spaced with a high C up to 3 in this case. We are going to look for each one of these, the full range of sigmas. We're only looking at 5 sigmas. This is a 5 by 5 flat grid, very common in just about every walk of life where a decision has to be made. Okay, let's go through the file now. Okay, we have this profile. Now let's see if there's this other variation, this other variation, this other variation. We have the suspect finally. Now, what does the suspect produce? All of these are joint probabilities. So if we have 103,000, or we have a 675,000, look at that, hardly at all. Okay, but it won't matter. We're looking for the combination of C and sigma, which gives us jointly, that means times. We multiply all these together, and jointly with the probability of seeing this C and this sigma, which we're thinking is, well, they're all equally probable here because we don't know any better. We compute that over here. We compute that over here. Each one of these is a product of one end to the other. And then we compute in the next column the product of all of these together times the probability of seeing both and both a particular C and a particular sigma. We sum these up and look at their relative contributions, and now we have a probability distribution. Now, this is also called Bayesian statistics. This is also called maximum likelihood in a sense. It's a fairly deep approach to estimation, but what we're looking for is the C and sigma combination that gives us the highest plausibility of being consistent with all this lovely data that we have. And this is actually a very small data sample. All of this data, most plausible. And to do that, and of course we can, here's our formula down here for our lovely probability distribution. It's more, get the experience of doing this. Okay. In other courses, you learn a great deal more than this, but I wanted you to get the idea that I can even simulate what's the right parameter value. That's the idea I really wanted to get across. Now, if you want to get deeply into this, great. Otherwise, you're going to have to take it on faith. Faith is really important here, but it's justified true belief that this works. We're making a robot here anyways. I keep talking about that in other courses too. I unpacked this whole thing here for you, so look at it. But we have 25 hypotheses, and here's our distribution again for reference. We're making 300 joint probability calculations, everything from a low C to a high C, and I give you a calculation here. Please try it. Please see that they work. But also you got to understand that a both and condition in probability means multiplying it. That this happens 50% of the time, and this happens 50% of the time, means that when they both happen together, it's 0.5 times 0.5, or 25% of the time, right? That is for them both to happen. That's the thing we got to get into our mind. We have all those, and then we sort them into this associative file. Again, using index and match to get the job done. We see that the maximum probability of sigma and the maximum probability of C that are consistent happens right here. So we have found our parameters, 13.5, and C is 2. We can slice this grid up more finely if we want to get a more precise number, but that's counting how many ethereal beings can we find on a head of a pin. That's not going to be very useful. The joints are jumping for sure. And I take all of that and I do a weighted average to find the mean C, the mean sigma, the standard deviation of C, the standard deviation of sigma. This is straight out of elementary statistics. And then something else called covariance. Covariance gives us, again, foundations of statistics. Take covariance, divide it by, that's just the weighted average of the deviation squared. It gives you the plus and minus. This is all plus, but not very big, of how C and sigma are related to one another. And they are related. They're just like the waiting times last week are very much related together. Like last week we did intercept and slope. They're related. How are they related? Because they have a joint probability distribution that is not equal to 0. If they were unrelated, there would be no probability of ever seeing the two together, ever. And here there is. It's in the data. We're teasing out of the data an awful lot of insight about the data. That volatility is correlated with this shape, and this shape is the thing that gives rise to high kurtosis. We're going to get a kurtosis of 14. 14 is greater than 3. 3 is what a normal distribution is, very thick tails. And nobody is going to bat an eyelash. Oh, no, no, no. Insurance companies are going to be all over this. Do they want to insure that big an event? No, they do not. They're going to call that an excess of loss event. We're not going to insure it. How do you insure it when it happens, other than throw yourself on the bankruptcy court? Okay, that's where we're going with this. And in the pandemic, we've seen this happen. Okay, so in this next frame, we have our calculations to 13.5. We can actually calculate a standard deviation of C and a standard deviation of sigma, and actually create weird kinds of probability intervals on the assumption that these things are normally distributed in the end. The parameters are normally distributed. Now they come from, because they're averages, they come from a distribution that is absolutely not normally distributed. Okay. Or distributed. Here we go. I'm sorry, I've been talking UK. So we have 6 years of claims to play with that we have to worry about. Okay, it's actually year 2 to year 7. Because they want to construct a fund. They have to go out far enough into the future to see how much I have to invest in year 1 to cover stuff as it flows out over the 6 years. And that's a typical number. 5, 6 years is typical for a lot of situations. Talent, for example, the hunt for talent and the optimization of the right talent for your company usually has that kind of same idea. And this model actually can be used to help get a handle on that. Look at these lovely functions here, just like last week, very complicated, but I'm incorporating the fact that there is a 0.8 correlation between C and sigma, between volatility and something that will give us the volatility of volatility, the kurtosis. They are very much related, okay? And for each year, we get a different version of C and a different version of sigma, just like we did for the 20 eateries last week. Exactly. So we're using exactly the same technology again. Well, because it works, it applies. Now, can I generate DPD variates? I can't. If I have a rand, which is a uniform distribution, I know C and I know sigma, and I know the threshold, which is about 100. I can generate these lovely distributions, and I do it right here. Okay, that's where it's happening. Okay, but I also do something else here. I'm going to set a maximum claim to 2 times the largest claim in the data itself. I could set it at 3 or 4. You can say, now I'm kludging it. John Kluge, yes, John Kluge, who invented the thing that could paint buses so you could still look out through the window, but advertise to the world all sorts of neat things. John Kluge. Yeah, I'm shoehorning something in, absolutely. But I'm practical here. If I allow anything to be sampled, I will allow a claim of 375 million, which is not reasonable, okay? Not reasonable. In that case, everybody goes home. Not reasonable. Well, everybody did go home with the pandemic, so maybe it is reasonable. And then I set myself up for success in doing a optimization. Now let's set that up next. Watch this. And I'm only going to spend a couple of minutes on this because I want to come back to this again. So here is, I'm calling it a sinking feeling because it comes from a sinking fun application that is more than a little interesting. In fact, this looks so complicated, I think we'll come back to it in the second part. Right now, focus on being able to project There are our projections right here, these claims. Being able to project a claim. Now, one is not going to be enough. One projection is not going to be enough. We're going to want to know what investment schemes we're going to need across time, given that this projection may change. And that's a probability distribution. And a distribution will go vis-a-vis each of these parameters for different years. All of this is correlated all together. They all have joint probabilities in common. In fact, C is 0.8 correlated with sigma. So we need to incorporate all of that into our analysis. And the sinking fund down here is fascinating. You get your hands on the workbook. We have investments here, each of which start and end at different times with different returns. And we can see that in this particular situation, we're only needing capital starting at time one of this and more capital down here. And this is the total capital in year one. Why is that? We have a very, very simple requirement for claims in this particular instance. But all of this will get sorted out in the next round. We'll look forward to seeing you there. Thanks very much once again for your kind attention and your patience.